why it's not in the PowerPoints, but it's something that we need to do. It's something we refer to as duty cycle. Anybody know what the duty cycle is? A duty cycle. And it's not vulgar. It's not what you think. Duty cycle. But what we do, it's becoming more and more popular to control things with solid state devices that are either off or on. So the problem we have is that, especially in DC motors and also AC motors, it's becoming the predominant way of driving AC motors. I don't know if you've heard of variable speed controls. Variable speed controls use a method that we call pulse width modulation, which basically deals with duty cycles. So this is something the book ought to cover. And here I'm in the motor controls folder instead of the digital. So we'll look at what we call, now we know some terms, right? We know everybody okay with frequency. What's frequency? First of all, what's a cycle? Not a rate. One repetition. It's just like a laundry cycle. A day is a cycle, right? An hour is a cycle. Hours coming up. We have 60 minutes an hour. One hour gets over, what happened? The other one starts. And then 1 hour gets over, the other starts, right? You understand? So a cycle is one repetition of a repetitive waveform. No, they're not the same thing. Cycle, the period is the time it takes for a cycle. Okay, you understand?
60 minutes.
Yeah. So an hour would be a cycle. Then how much time is in an hour? Well, that would be kind of like the period, right? You understand? So what is the time for an hour? So we have 24 hours in a day. Okay, so an hour would be, y'all understand that? And then the time for each hour would be what the period is. So the cycle is one repetition of a pulsating, of a repetitive waveform. The period is the time it takes for one cycle. And what's the frequency? Morrison's not going to answer anymore. So. There you go. I love it. Go ahead. So what's the frequency? What? That's perfect, right? The rate of the cycles. Okay, good. So what we can do is we can change the duty cycle without changing the frequency. So what we're doing, the duty cycle is the percent of the period that a waveform is high. So I've got this chart out here so I can draw them and keep straight lines. So if I come over here and draw some waveforms, and we'll start off like this. So I'll make it real easy, and I'll do it in a color that we can see. Okay. So let's say we come up, and I'm gonna go over one, and I'm gonna come down, and I'm gonna go over one, and I'm gonna go up one, and I'm gonna go down one, and up one, and down one. And let's do it a little different. How many I got across here? 10. So what I'm gonna do is just draw one cycle, and I'm gonna spread it out across the whole thing, because that way it'll be easier for you to see what a period is. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. So what I'm going to do is I'm going to come up and go over 5. 1, 2, 3, 4, 5. And then I'm going to go down and go to 5. 1, 2, 3, 4, 5. And then what would happen? It would go up. Okay. Now, there's 10 divisions. So this is high 5 divisions. This is low 5 divisions. Okay. So if we counted these in milliseconds, what we do, the duty cycle is basically equal to the pulse width. We call this the pulse width over the period. So the period would be 10, right? You understand? The pulse would be, the width of the pulse would be 5. So this would be a 0.5, but we don't give it that way, we would say 50%. So that'd be a 50% duty cycle. Yeah, yeah, 50%. Okay, I understand. Yes or no? So this is what we call square wave. This is what we call square wave. A lot of people misname the digital pulses, and they'll call them square waves when they're not square waves. Okay. This particular one is what we call it, is technically referred to as a square wave. So a square wave would have a 50% duty cycle, which means 1/2 of the period. No matter what the period is, 1/2 of the period. Huh? What's that?
I said period point blank, it would have 50%.
A square wave.
Square wave.
Correctly would be called a pulse waveform that has a 50% duty cycle. But you got a lot of people out there that just calls digital, they call digital clocks square waves, and they might not be square waves. Y'all understand what I'm saying? So, you know, you can't say period and always or anything like that. It's just like we use the term ground all the time. But ground is one of the most misused terms in electricity. Y'all understand that? Because to have a ground, you have to have a copper rod dug down in the ground, and you have to have a cable connected to that. But you can go out and talk to a mechanic or anybody that works on cars, and they'll call the black lead the ground wire. But it's not the ground wire. It's a common. It's the common wire. It's not the ground wire. And we have two different symbols, one for ground and one for common. But, you know, if I was out there working for my boss and he said, well, you know, the ground's disconnected, I wouldn't say, well, that's not the ground, that's the common, right? That'd be almost as bad as talking bad about his wife, right? A lot of people don't like to be corrected. And so it's became the norm of for the trade for just about anybody. You call a ground a what? I mean, a common a ground. So we call the common wire ground. So, you know, so saying that it's wrong to do it is not really. But this is technically, truly what a square wave is. Now, know what? So this is 10 wide. Now, watch what I'm doing. What I'm going to do is I'm going to erase all this, and what I'm going to do now is I'm going to come over here and I'm going to go 1, 2, 3, 4, and then I'm going to go 1, 2, 3, 4, 5, 6. Now the period is still 10 milliseconds. The frequency has not changed. So now we would have 4 over 10, right? And this would be 40% duty cycle. Now, what just happened, though, what would you think about the average DC voltage this would represent? Well, purity, if it's solid DC and this is 10 volts, then that's 10 volts, right? You understand? But if I start doing things like this, then the average DC is going to vary because everything's going to average this out. DC is an average, right? You understand? So right now, if I had this firing a DC motor, the DC motor would just slow down because it don't see the voltage on all the time, right? You understand? That makes sense. So this would be 40%, but I'm not changing the frequency. If you don't change the period, you don't change the what? The frequency. Okay. So I could come over here, and this is real easy to see. We'd have to measure this with an oscilloscope. So if I came over and did this, and this is 10, and then of course this would be a 20% duty cycle. So the motor would slow down, right? In fact, you can calculate the average DC voltage. You just take the maximum voltage and multiply it by the duty cycle, and that'll give you the average voltage. So this is the problem is when we control a DC motor, all we got to do is control the voltage. So one form we can do is we can come over here and put a rheostat in series with it. Now the problem with that is that if you run through a resistor drops voltage, and P is equal to I squared over R. Now understand, so the power in the resistor varies with the square of the current. So now I've got something up there eating up power that's not really doing any work, not doing any electrical work. Well, to do it with solid state for a long time, we use SCRs, but we're not going to get into that. Let's try to do it with a transistor. So I try to do it with a transistor. So there's another device we could do this with, but it's becoming less and less popular. So this is my DC motor. I could come over here and do it with a transistor. Now the problem with that is that we're operating in the active region. When we operate in the active region, it acts like a rheostat. So if it drops a voltage, you know, so if I've got 100 volts over here and I want my motor's a 100 volt motor, I put 50 volts over there, then the transistor's going to have to drop 50 volts. If it drops 50 volts and there's current flow through it, it's still, now we got what? Now we got V times I. So it's still going to produce a lot of power. Now what if we didn't operate that transistor in the active region? What if we switched it off and switched it on? Switch it off, switch it on. And we vary the amount of time we leave it on. Well, what happens is it's a saturated transistor. A saturated transistor drops almost no voltage. So now V is almost zero. It's not quite zero. And 0 times I always ends up to be 0 power. Now transistors will never drop 0, so they will get hot, but they wouldn't get as hot as if we were operating in the active region. So we use a real high frequency. We don't use a real low frequency, which has a real short period. And what they do is they vary the duty cycle. And if you ever heard about pulse width modulation, that's exactly what that is. All they're doing is digitally doing what? Pulsing that motor, but what are they doing to change the speed? They're changing the what? Duty cycle. That's what pulse width modulation is. So this is one thing we should have talked when we talked about the signals, because this is a really common term. You'll hear if you're in AC drives, you'll hear pulse width. That's the way they do it. So if I had a negative DC and a positive DC, and I did pulse width modulation, what we could do is we could actually, with pulse width modulation, we could actually vary the frequency to the motor, even though it's DC, but it's minus DC and positive DC, right? And we could also vary the frequency, and that's what we have to do. So to control an AC motor, so a DC motor is a little easier to control, because all you got to do on a DC motor is control the voltage. To control the speed of an AC motor, you got to vary the voltage and the frequency. So the AC motor tries to run at a certain frequency, but if you don't adjust the motor when you adjust the frequency, there's something called X sub L that comes into play. So what happens, if you double the frequency, you have to double the voltage to the motor. If you half the frequency, you got to half the voltage to the motor to make it run at the right speed. If you don't, it won't work. But, you know, with electronics and computers, so for years, if we wanted to control the speed of a motor, it was a DC motor. But with the advent of some of the all the electronics we have now, the predominant speed control now is AC motors, because AC motors cost so much less per horsepower. So with a DC drive, I had to have the drive to control the DC motor. I had to have the electronics control the DC motor. So we still have the drive, but now we're controlling AC motors using pulse width modulation. So yeah, if you get into drives, if you get into solid state drives and into any new installation, it's going to be an AC motor. And why? Because AC motors are so much cheaper per horsepower. A DC motor, the rotor on a DC motor has to be wound. So it's got a lot of copper in it. And plus, it's electromagnetic in the middle. So to transfer the energy over to the electromagnet, we have to have what we call a commutator, which is a metal segmented thing back there, and it's got brushes riding on it. And so now we've added more mechanics to the thing. So DC motors require a lot of preventive maintenance. You got to go in and maintain those brushes, which is what's on your alternator. So that's why your alternator goes out every once in a while. And most of the time, you know, you go out and buy a new alternator, and it's, you know, $200-300, and they send it off down to Chancey's down there, and they replace the brushes and turn around and sell them. It's just the brushes that wore out. We might have a DC motor here that y'all can actually look in and see the commutator. This is not a DC motor. This is a universal motor. And guess what's wrong with this? The brushes went out on the thing. But when we pass this around, you can see where the brushes used to be. And you can see where it burned up on the commutator. So we do have one motor called a universal motor that we can run it on both AC and DC. So it has that assembly. So back here in the very back, this thing just burned up back in the back. This is the commutator. And these on the side, these are the brush holders. And the brush holders are gone. You can see what happened is the brushes wore out. And then the brushes dug into the commutator. This is still repairable, by the way. We have a burnishing tool that we can spin the motor and then burnish this off real good and then put new brushes in it. We could probably... This is off a compressor, by the way. Not a big one. So everybody okay on duty? So what's the duty cycle? Duty cycle is the percent of period that frequency is high. We can simulate this, or we can do this with our function generator. Let me look at my function generator. So a function generator is a device that generates multiple types of signals. And we have 4 categories of signals that we're going to deal with in electronics. So what's nice about an oscilloscope? An oscilloscope shows us exactly what's there. This is a waveform that we call a sine wave. And we're not going to get into in this class, but we're going to take AC or even solid state. What we're doing is we're looking at a waveform, and the scope is picking up something over here, and it's coming in the scope, and the scope is not synchronized. So what we have on a scope is we have something referred to the trigger. And what the trigger does, it makes the scope look at a certain voltage. So notice when I start moving this, see the white line coming there? And this is the trigger. So I'm going to set it at a certain voltage. So as long as it's outside the voltage, the scope will trigger on it. You see what happens when it don't trigger? It just wiggles around. If I move the line into the signal, then everything's going to freeze. What do we call this? Trigger. You have to, this is a 2-channel scope. You can only trigger off one channel. So right now we have channel 1 selected. So I have my trigger set up to trigger on the channel. So we call this a sine wave. This is what Alabama Power generation is. Now this is not Alabama Power. This is electron. What advantage does DC have over AC? Did we talk about that in this class? We got 2 types of power out there. We have DC and we have AC, right? What y'all just taking solid state? What's the advantage of DC over AC? Yeah, we can not control electronically control. So we electronically control DC. So that means your TV, even though you plug it into Alabama Power, it operates off of DC. Of course, you know your car operates off of DC. But your radios, your microwaves, anything got a digital readout, you know, all your computers and everything operate off DC. So what we have is we have these units that we have. So this guy here operates off a battery. A battery generates DC. And then, of course, we've got this guy right here we call these power supplies. Here's Alabama Power. Here's DC. Okay, y'all understand that? In solid state, you'll get it. When you take solid state, if you take solid state, you'll get into power supplies a little bit. So this guy, though, so what this guy does is take DC, AC, converts it to DC, and then regenerates AC from DC. So we can change the frequency on this. This is the function generator. So notice the frequency's going up. So, and this is a cycle. So the length here is the amount of time it takes, right? So if these things getting closer together, it means the time's going down, so frequency's going up. But see, I can control the frequency, and I can control the amplitude. And of course, we can't do that with Alabama Power, right? You understand that? Okay. See, my trigger now is up here. That's that line. See the little yellow dot right there? And I've got outside my trigger, so what did my scope just, it went out of sync. So what do I need to do? I'm going to come over my trigger knob and move it, and all I got to do is get down there. Now, to measure this thing, what we do is the scope measures time, and it measures volts. So volts are up and down. time is across. So what we can do, the ultimate goal to get the best possible measurement is to make this as big as you possibly can without it going off the screen, because that's when your scope is the most accurate. So this right here sets what we call the vote per division. Now when we talk about divisions, we're not talking about these little tiny dashes, we're talking about these big dashes right here. And this scope displays down here. So right now I have it on 10 volts per division. So now I have it on 1 volt per division. So what would be our voltage? Can anybody see it? Just kind of, y'all can see the major divisions. Yeah. So this is in the center down here, so it's kind of hard to see, but we can see that 1, 2, 3, 4, 5, 6, 7, about 8 volts. Peak, what we call peak. That makes sense? Huh? Peak to peak. Because we're making our measurements from here to here. So this voltage right here we call VP. We don't have to know in this class. This voltage from here to here we call peak to peak. Now when you put your meter on this, it's not going to measure that, because your meter is going to come in and not average it. It's going to, because this goes to 0 right here and it does no work. So in DC, in solid state, we'll learn how to actually see what the meter will read. The meter's going to read a lot less. The meter would read exactly 70.7% of what's up there. Why, we're not going to talk about it. And to measure time, what I would do is I would spread this out until as long as I can see one cycle. And by the way, we can move it around. So this guy right here is what we call the horizontal position right here. So notice what I can do. I can move it around. And then what I'm trying to do is I'm trying to get the start of this. Now, a cycle, well, all you try to do is try to get a repetition, right? So you don't have to get it where it crosses going positive or where it crosses going negative. So my time is 250 microseconds per division. This is one you'll probably have to use a calculator on. I couldn't even do that. Sort of this. So that would be 250. That would be 500. That would be 750. This would be 1,000, right? This would be 1,050. See that? Normally what we do is count the divisions. 1, 2, 3, 4, 5, 6, 7, 8. 8.1, and then we would multiply it by this. 250 microseconds. Now what would that give me? Well, that would give me the time. Or the period. If I know the period, what would be the frequency? So y'all see what I did? Because y'all going to be using this thing. So if you got any questions, you need to ask me. We're going to be using an oscilloscope. Why are we going to be using an oscilloscope? Because oscilloscope shows you what's there. A meter is going to average out anything. So if I took that meter and put it across a pulse waveform, it's going to give me an average. It's going to be the maximum voltage times the duty cycle. That's what it's going to give me. If I put it on AC, it's going to give me, we don't call it an average, it gives me what we call an effective voltage. But the scope shows me what's there. Okay. So what we're saying is that, let me get the calculator up here. Here it is. Okay. So if we know the frequency, if we know the period, ain't that neat? I don't know what's going on. It's cool. If we know the period, so what I have here is I have 250 microseconds for every major division. But then between every major division, we have 5 minor divisions. Can y'all see them? So what I would do is I would come up here and count the major divisions. Now the minor divisions, if I'm counting in ones, we got 5 minor divisions, and each minor division is going to be worth a 0.2. Y'all understand that? So 1 divided by 5 is 0.2. So I'd come up here and I'd start counting. So I cross it where I move it with this until I cross it on a vertical line. So this is the position control. I come over here and count. 1, 2, 3, 4, 5, 6, 7, 8.2. I mean 0.4. 8.4. Because I got 2 minor divisions. So I would say what? I'd say 8.4 That's the number of divisions, right? Now, once you use a scope a long time, you'll see this. You can do the time in your head. And how much is it per division? Then I would say times, right? 250 times 10 to the minus 6. Y'all understand that? Have I lost anybody? Huh? What we're trying to do is we're trying to figure time. Our scope measures time. Now, first of all, you got to know when we say time per division. So that means this division right here, it says 250, y'all can't see it, 250 microseconds per every major division. Okay, y'all understand? So what I got on my scope is I've got this. I've got this grid. And then what we do is we subdivide this 1, 2, 3, 4. So that's 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5. These should be spaced out even. 1, 2, 3, 4, 5. So if this right here is equal to a 1, because we're counting in ones, what would each one of these be equal to? You got to come up with one, guys. Huh? 0.2. It can't be 0.1 because if I go 0.1, so it'd be 0.1. I'm still at 0.5. So you're right, Marie. So each one of these would be equal to 0.2. Okay. So I came over here and I counted. So I've got this waveform and a cycle, and I went 1, 2, 3, 4, 5, 6. And then when I come down, this guy here crosses over here, and it crosses at the second minor division. Okay, so that would be 6.4 divisions. Okay, y'all understand? Okay, now I say, okay, no matter what it does, this is one way we can do it. And like I said, if you use a scope for a long time, you can do these 250s in your head. So, you know, if it's 250, then every 2 would be 500, right? You understand? And so you could do it that way. It would be pretty fast. But while you're learning it, this is the best way to do it. So this is the number of divisions. Now I say, okay, what is the time per division? Well, the time per division is 250 microseconds. So if it's 250 microseconds for every division, and I go through 6.4 divisions, then the way I would do the time is I would do what? I would take my calculator, get the number of divisions. What's the number of divisions? Clear. The number of divisions is 6.4. Does everybody understand that? Then I would multiply it by the speed per division. So I'd say times 250 times 10 to the minus 6. And then I would say equal. So that's 1.6 milliseconds. And then how do I find the frequency? So if I want to know the frequency, we take the reciprocal of the period. So somewhere on your calculator, if you got a scientific calculator, is a reciprocal key. And you're going to learn in electronics, we use a reciprocal all the time. So instead, you could say 1 divided by, but you've already got that number. So now what would you have to do? You'd have to put that in memory. Then you'd have to say 1 divided. So, but we got a reciprocal key. By the way, if it's got your calculator might have x to the minus 1. If you raise any number to the minus 1, it's the reciprocal. So I'm gonna hit that. So that's 625 hertz. One, 2, 3, 4, 5. I did wrong. Let me turn it back over. I was fixing to say. I was going to show y'all how accurate this was, but we screwed up a little bit. Let's recount the divisions. So y'all do it. So that wasn't right. So here's 1, 2, 3, 4, 5, 6, 7, 8.4. Yeah. So y'all do it for me. So this worked out to be good. So, but it's still 250 per division, right? Okay, but we're looking at the frequency, so take the reciprocal of it for me. Now you got to understand a scope is, these minor divisions get real hard to read sometimes. So what I'm going to do is I'm going to flip it back over on my camera, and this function generator has, oh, it's already on there. This function generator has a frequency counter in it. We calculated 465. It's actually 494, so that's not too bad, right? But you got to understand a scope is not extremely accurate, because when you get to the minor divisions, what you got to do is figure out exactly where that thing crosses. If it crosses between a minor division, then you got to guesstimate it, right? And the voltage is the same way. So if I come over here and look at the voltage, I have it on 1 volt per division. Now what happens when we look at these waveforms like this, where it splits in the top and splits at the bottom, what we need to do is come over here and take this position knob. You notice what I'm going to do. I'm going to adjust it to the bottom goes down and touches a line this way. Now it's still AC, it's just I've changed the ground reference of the scope right there. So now we can measure, and then I move this one. What I usually do is move this one until I get to the center. So how many divisions do I have, guys? One, 2, 3, 4, 5, 6.248. 6.8 divisions. Now all I got to do is figure out what my volts are my volts per division is. So right down here it says that's 1 volt per division. So now we don't have to do any math, so it's what? 6.8 volts. So what you do to change your volts per division is you use this knob right here. And your ultimate goal is to make it as big as you possibly can make it until still keep it on the screen. So that's the best. I can't do that, right? Because I can't see the tops. Okay. This allows us to adjust the vertical position. So this is actually AC that we're looking at. How do I know it's AC? Because this is 0 volts, and we have a positive and we have a negative. So I adjust the time with this knob over here. So this is time per division. So notice what we're trying to do here. So right now I couldn't measure the period because my scope is going too slow. So I need to speed my scope up, which means it's going to spread it out. So what I'm going to do is start turning this knob right here, until I get, so I can't measure it there, right? You understand? Because I can only see one part of the cycle. So what you do is you'll slow it down until you can see a whole cycle. Because you can't measure the period unless you can see a whole cycle. But if I tried to measure the period here, that would be impossible, right? So if you see this kind of stuff, then the scope is going too slow. So you need to speed it up. If you see this kind of stuff, and this gives you problems because you can get the speed of the scope turned up so high, it looks like you're looking at a straight line. But it's not a straight line. It's just that the scope is spreading it out so far, and the slope of the waveform, we got it going so fast, it's just showing me the section of the wave, right? So be careful with that. We run into that all the time in electronics, where they have the speed set wrong, and they'll draw it as DC, and it's actually AC. So let's put it on a pulse waveform. So this is a pulse waveform. This is AC. So in our class, we're going to have to get off that. And so what I'm going to do now is that we have a knob on our function generator called duty cycle right here. And then we got where we can adjust this right here, duty cycle. And we can come up here, we can change the duty cycle. But notice, this side right here is not changing. So we're not changing the frequency, we're changing the what? The duty cycle. So see, the frequency is not changing. If the frequency is not changing, then the rising edge of this pulse and the rise, so that's one cycle. So what we're doing now is we're coming over here and we're varying the width. And what we'll do later on for y'all guys is we'll hook up a DC motor to this thing. This function generator can't run a DC motor, but we can hook this up to a transistor. And a transistor gives us current gain, and we can control the speed of a DC motor. It's so neat. And all we're doing is changing the duty cycle. We're not changing the voltage. The voltage stays at the peak voltage. And all we're doing is changing the duty cycle, and the motor changes speed. And this is a very popular way now to control a DC motor. Pulse width, what we call it pulse width modulation. So what is pulse width? And this is the other waveform that we deal with in AC. We call this a triangle wave. I wonder how I got that name. Right. And then we got this waveform right here. What do you think they call that? Huh? Sawtooth. This is sawtooth waveform. Sawtooth. It looks like the tooth of a saw. So we got these names. So one of them's a pulse waveform, but just about everybody's going to call it a square wave. But we know now a square wave has actually got 50% duty cycle. But just about everybody calls this thing here. They call this thing just about everybody calls this, even though that is not a square wave, they call it a square wave. Are you okay? So all a sawtooth is a triangle waveform with a different duty cycle. That's all it is. Now the problem we have in digital is that our digital devices operate on DC signals, and this right here is an AC signal. So later on I'll show you how to make the function generator. Y'all know why it's AC? Because here's 0 volts. So anything above here is plus. Anywhere down here is minus. So we'll have to figure out how to make this thing generate DC for us. We'll show you how to do that. So I'm going to do something called DC offset. I'm going to put that in there. And then I'm going to adjust it. Now this is, now what's wrong with the scope? It's not triggered. So what am I going to do? I'm going to come over here and take the trigger control, which is right here, and I'm going to move it until that white line gets into the signal. And there it is. It just froze it, right? And then, so this is DC. Notice here's 0 now. But what I did with my function generator is I put in what we call a DC offset. So that's this control right here, DC offset. I push that in. And then we have a DC offset control. So when you do that, you can actually make something that generates AC and actually do what? Generate DC. So this is what we're going to have to do. And we'll play around with that a little more. But what's nice about a scope, if I was to put a meter on this thing, or even if I put a logic probe on this thing. So if I put a logic probe on this signal, what's the logic probe going to show me? I can't do it. We don't have a common power supply. I'd have to make a common. I'd have to make my meter common with my power supply. Okay. But if we put our logic probe on this thing, you know logic probe, what's that? Passed them around the other day. Yeah, so we call these logic probes. And these guys work really, really great on low frequencies. But high frequencies, what's going to happen is you have to interpret them. So when you operate on a high frequency, what's going to happen is the pulse light's going to come on, and both lights are going to come on. If the red light is brighter than the green light, it means it's got over a 50% duty cycle. If the green light is brighter than the red light, it means it's got less than a 50% duty cycle. So that's about all you can tell. You can't tell the frequency, you can't tell the time, you can't tell the voltage. You know the voltages are legal because if the voltages are not legal, the lights won't come on. So if you don't get a legal low level, the green light won't come on. If you don't get a legal high level, the red light won't come on. But the problem is it might be red all the time, and we might get a pulse that's a legal low, but this light flashes before we see it, right? You understand? So then they got a pulse light on here that if it blinks, it means it changed level. So you can tell if you got a pulse. These guys, I don't know what they cost now. We haven't bought them in a long time. We could look them up on like Jamico or something like that. We got some. A Radio Shack used to sell one that was pretty cheap. It was a nice one. But every time it saw a high, it would beep at you. Beep, beep. And everybody in the class went down there and bought one. We talked digital. And oh man, Them things like to drove me crazy. Unfortunately, we don't have Radio Shack. Is there a Radio Shack around here anywhere anymore?
Yeah, all right.
I thought the one on Green Springs closed. Is it still open? Last time I heard it was open, but then somebody told me it was closed. Radio Shack used to be really, really neat. We used to go in there all the time. And then Circuit City came out, and Circuit City started selling all these appliances and all this other garbage. So Radio Shack started doing that, and they stopped being an electronics store into they even sold cell phones. Now it was nice when they first did that because they got rid of most of our electronic parts, and they sold them for nothing. So I stocked up on it, but harder now to find electronic parts than it's probably ever been, except through mail order, and that's what's happened to all our parts places. Just like the brick and mortar stores, is there being a lot of people starting to go online and not go to stores anymore. So there's still a lot of places to get electronic parts and to get these ICs and everything, but okay, guys. So what was so duty cycle? Everybody okay there? We use this in a technique called pulse width modulation. These are used in both DC drives, and they're also used in variable speed AC drives. Look up variable speed AC drives, and you'll see it's really, really neat the way they use DC to generate AC, not only at a different frequency, but also at a different voltage. So what else was we looking at? By the way, I went over and got the gates. So on that handout, everybody got one, right? So we got somebody that's not here. Is Barry in it? Barry and Jackson. We got two people that's not here. So what we're doing on that sheet, of course, is right now we're looking on the left-hand side, and we're not looking at the Boolean equations yet. So every gate's got a Boolean equation. A Boolean equation, actually. I turned off my camera. I did it. So this is our study guide. So these are our basic gates. So this is an AND, right? An OR, an AND, a NOR, and a NOT. The circuit is called an inverter, but the logic is called a NOT. So that's the only gate that works like that. Here's our logic. Here's our expressions that we need to start learning. And then these are what we call positive logic. These are what we call negative logic. Y'all know why they're called positive and negative? Because we look at what we call the active state of the input. So notice on all these gates, the inputs are high active. When we look at these gates, they got bubble on the input, so these inputs are low active. So we call this negative logic. It's not negative voltage, it's referred to as negative logic. So we refer to this as positive and we refer to this as negative. And later on we'll understand what's going on. So if you look at those schematics in the back of the textbook, you'll see a lot of these symbols that's got bubbles on the input. And we'll see why they do that. And hopefully if you go to work on these, the place you work for whoever supplies the schematics does that, because they'll really help you in your troubleshooting. So we're looking at basic gates. So how many basic gates do we have? You guys, we've got 5 basic gates, right? All logic is made from them 5 basic gates. So when we start combining the gates into more complex circuits, we refer to those as combinational logic. So all these counters and these multiplexers, when you start looking through the book, all the different things that we do is that way. So if all inputs are high, the outputs will be high. We're talking about a what? What's that the phrase for? Huh? No, if you use the term all, it's and, any is or. Okay? So this is the long drawn out phrase. If all inputs are high, the output would be high. So what we do is we cut that down a lot. And so we put the inputs on the left, the outputs on the right. We say all highs equal a high. Now understand that? Are we okay? And of course, this is a symbol for a 2-input AND gate. How many inputs can an AND gate have? How many inputs can it have? Yeah, a minimum of 2. Y'all understand that? A minimum of 2. If I'm making diode logic, I could put as many inputs as I wanted. It just depends on how many diodes I have. Of course, if we buy a circuit that's already put together, so if you go out and buy one, then you're dependent on what the company makes, right? We're going to be dealing with a 7400, which is we call it a quad 2-input NAND gate. So that means quad means there's how many? 4 in there. Each one of them has 2 inputs and 1 output. So each one of them requires 3 pins. For some reason, when we start trying to figure out how many of these guys we can put on a chip, a lot of people forget about the input. So we don't specify the number of so on the specification, we don't specify the number of outputs because all the outputs are going to be 1. So when we say a 2-input NAND gate, we say that would take 3 pins because 2 for the what? 2 for the inputs and 1 for the output. This is the truth table, which we've already looked at. Truth tables are fun as long as we don't get over 4 inputs, right? Because these things vary with the power of 2. So that's why learning that all highs equal a high is a lot better than dealing with truth tables. But this is all highs get a high. So all highs to get a high. Well, if any input is low, the output will be low. The OR gate, the output is high whenever inputs A or B is high or both are high. And this, I think these are the same 3-5. I think these are the same truth table. Now, this is what this is what we're starting on. So every circuit has an equation, a Boolean equation that goes with it. So now this symbol for multiplication or for AND is out because a lot of times we call the inputs X. But what we can do is the symbols that we use in mathematics to do multiplication is a symbol that represents AND in logic. So if you saw this right here and it's logic, you're not going to say A times B. You're going to say what? A and B. A and B. That makes sense. So you got to understand these are symbols. In math, we have plus and minus symbols, but you're going to run into those symbols all over the place that don't mean positive and negative. So on a differential interface, the uninverted signal is called this, the inverted signal is called that. So if you ever look at the pin out of a USB cable, that's what it's going to label. It's going to be labeled plus and minus. And if you try to power it up off those plus and minus signal leads, you're going to have problems because that's your signal, right? You understand? So we got to understand that these symbols can mean different things. They're symbols. It's just like in the early days, these are nothing but symbols, but we started out using that for a while, and now it's a symbol for a smiley face, right? So it's a symbol. Of course, now we actually have what they call emoticons, but in the old days, you actually created them out of it's just the symbols that we already had available on our keyboard. So the symbol, all the symbols that we use for multiplication, so they don't show one, they don't show the dot. So X is equal to A and B, that's a legal symbol. And of course this right here is legal to indicate an and, right? We can use parentheses to indicate an and, or the asterisk can indicate an and. This came back from the early days of computers when we were writing programs. We couldn't use this to indicate multiplication because that was a letter. So what they did is they couldn't do a dot in the center. So the old keyboards didn't have a dot in the center, right? There was no symbol. So what they came up with is to use an asterisk to indicate multiplication, and that's still true in a lot of languages, by the way. Can't have more than 2 inputs. Do y'all understand that? So if I come over here and got this, 1, 2, 3, and call this M, K, T, and call this Z, what would be the equation? Now, the normal tendency is for people to do this. And mathematically, that's incorrect. You never put what you're solving for on the right? What you're solving for always goes on the left. Everybody understand that? But this is normal tendency for people because the symbols are drawn from left to right, but the equation is from right to left. Okay. So the true equation would be Z equals MKT. Or we could have just well have done what? We could have said Z equals M and K and T. Or we could say Z is equal to M, K, T, right? Or we could have did asterisks. All these are legal. Now, but the problem is people want to multiply. So we'll come over here and say Z is equal to A and A. And people in math want to call that A squared. That's not A squared. That's A and A. So there's no such thing. In Boolean algebra, there's no such thing as powers. There's no such thing as exponents. We don't have any squares. We don't have any roots. We don't have anything. Okay. We got these basic operations right here, right? So what we use for multiplication in math, we use that to represent and in logic, in Boolean. So what do we use for OR? This is and, but notice all they're doing in the textbook is showing you 2 inputs, and some people get the impression that all we have is 2 inputs. All we have is 2 inputs, right? But how many can they have? More than one. More than one. I'm sorry, more than 2. 2, we should say 2 or more. Right? So more than one's technically correct, but we're still saying 1. We should say 2 or more. Okay, Wesley put up the timeout sign, so that means it's time for a break. TTL, which is transistor logic, which is what we're going to predominantly be working with this term. We are going to be working with a type of logic called CMOS a little bit, but they represent different things for highs and lows. We know that TTL is, what's the legal levels? So what's TTL power zone? What's the power? 5 volts, plus or minus 5%, right? And then what's the legal high? 2.4. What's at least 2.4? What's a legal low? 400 millivolts or less. Okay. So, but what we have to do on this thing is we have to power it up. So I'm going to bring up my 5 volt supply, and I'm going to put some jumpers over here if I find some. So these pots, by the way, we don't use these. These take up a lot of room inside your trainer, and we use them for quite a few classes. And they're not real cheap. They're not real expensive, but they're not real cheap. So what we do is we give these out. So when you do the lab and it asks you to use one, you'll come and get it from me. Then when you get through with it, you're going to do what? You're going to bring it back. Everybody okay? So y'all know the pot has 3 legs on it. The 2 outsides we refer to as 1 and 2. 1 and 3. And this center one is 2. We call this the wiper. And what we do is we never vary the resistance between this guy. So what we do is we set up a voltage divider here. So an adjustable voltage divider. I've talked about voltage dividers in DC, right? Very important to understand that. So what we'll do is we'll come up here and we'll hook 5 volts into the thing. And then you're going to use a meter. If you don't have your meter, we got a bench meter. If you got your meter, I would refer you use your meter. Because the more you use your meter, the better it's going to be. If you don't have a meter, then of course in this class we have some bench meters over here. Can y'all see them? We're on the left hand side. The probes are over here. Y'all can use. We use bench meters because we don't have to keep batteries in. So we got some newer ones, but these work just fine. And I don't feel like going over there and hauling them over here. So what we'll do here is we have to power this up. So I'm going to power this up on 5 volts. And what I'm going to do is come over here to my little Hall effect and just jump over there. By the way, if you bought the 22. If you can find that, that's fine. If you can, I know the bookstore is not stocking it for some reason. So we got some that you can use. So what we do is we hook up across the outside. Can y'all see what I did? So I've got 5 volts across the thing between 1 and 3. And then what we can do is if I was to put a meter on this thing. So this is what we can do with a pot that we don't do with a rheostat. So what I'm going to do is take my meter and I'm going to hook it up to my circuit common, which is down here. Can't get on my pot over there. Okay. And then I'm going to take my red lead. I'm sorry guys, my stand broke off my meter, so I got to prop it up, so hopefully it won't fall. I've got it on DC volts, 40 volt scale because we have 5 volts available. And what I'm going to do right now is just pull out the wiper. This is only 5 volts, so we're not going to worry about getting shot. And I'm going to hook it up to here. And hopefully what you can see, if I can come over here. Put your meter on DC. So can y'all see what I got there now? I got what? 2.9. I can come up here and start turning this thing. Or try to anyway. Something's going on, guys. Check and see. So I'm going to turn the knob, and can you see what we're doing? So I can get any voltage. That's what a pot does for us. So we use a pot to control the voltage. We use a rheostat to control the current. So what we're going to do is, how do we hook these things up? Well, you got to power this thing up off the circuit under test. The red lead goes toward the positive. Black lead goes toward the negative. Right? Let me see if I can find another wire. I'm running out of places I can slip onto. So what we're going to do is we're going to see what turns this thing on and what turns it off. What voltage turns it on. So you're going to need a voltmeter. And what you're going to do is you're going to turn it until it comes on until the highlight comes on. And then you're going to record that voltage. Then you're going to turn it until the low light comes on. You're going to record that voltage. And then you're going to, where's my pot at? Right here. I'm just going to leave it up enough so I can get my logic probe on there. So a good way to check the logic probe is to see if it's hooked up right or getting power. Is to just touch it to your positive supply and see. So this is usually what we do. And then what I usually do is come and touch it to your common, and the low light should come on. So can y'all see that? So now I've checked my logic probe off. So I put it here to 5 volts, the high light came on. I come over here and moved it to 0 volts, the low light came on. And then what I'm going to do is I'm going to come over here and move it to the wiper. So right now it's seeing this as a what? A low, right? Okay. And then we'll start turning it. Now what's it seeing as? Well, yes or no, it's seeing it as invalid. So right now there's a voltage there, but it's inside that invalid range, right? So between 400 millivolts or about, you're going to see the logic probe is not going to adhere to that. So somewhere around 400, 500, 600 millivolts, the low light will come on. Then when we get up to 2.4 around that, the high light should come on. So right now we're in invalid region, which is it. So this is invalid, right? Understand, I don't have hooked up to anything. And I'll come over here and I'll turn it until the highlight comes on. Now when the highlight comes on, I'm gonna gotta be real slow. We're gonna wait till it first comes on, right? You understand? And then we're gonna record that voltage. And then what we're gonna do is you're gonna flip this over to CMOS, and then you're gonna come in and do those voltage levels on both. See what CMOS recognizes as a high and what CMOS recognizes as a low. So y'all see what y'all gonna do? Everybody okay? So I think this is the first thing you're going to do after you do the inventory. So the logic probes stay in there in the storage room on the back shelf. On the right, there's a brown tray labeled logic probes and pulsar probes. So that's where they stay stored at. So once you get through with the lab, then what do you need to do? You need to put it back. Are we okay? By the way, I got the rest of the parts for y'all's inventories, I think. I got the 74 154s. So let's look. Let me give out the second lab. So we're going to work on 2 labs. Y'all are almost through with the first one, right? I think the only thing y'all got to do is play around with the logic probe. So let me go ahead and pass out the second lab. See what we're going to do here. By the way, sometimes I forget to get it out. But what we have here, we have one of these plastic folders. It's got ECT127 on it, digital. That's the class y'all taking. And inside this will be the blank level. Okay, y'all understand that? And the sign-off sheet will be on top of it. And you're ready for the sign. Everybody understand that? So lab 2's coming around. Dang it. Had that big old transformer on there, too. And if your partner's not here tonight, don't worry about it. That's their responsibility. It's not yours. So you work just like they're. It don't make any difference, right? And we hear that all the time. I'm gonna go home. My partner's not here. Well, your partner's not getting your grades, right? Huh? It's the same kind of lab. Well, this is lab 2, right? If you got an experiment 1, you're supposed to get an experiment 2. I don't know where that one came. This is, we had, Kyle wasn't here. And it was left on the stack. Sorry, go back. It was left on the stack. Now wait up, let's talk about what you're going to do with this lab. So we answered the questions now, right? And then hopefully when y'all go to lab, there shouldn't be many questions. So now's the time to ask you questions. When y'all doing labs, it's my time to ask questions. So if you don't understand what's going on now, you need to let me know. Y'all right? Understand? So this is lab 2. This might be the lab where y'all are going to do this. So let me wait on my computer.